last class we talked about average and instantaneous velocity. We're going to be talking about that more again today. So this is the exact same setup as we looked at before. There's a car driving from one city to another. The cities are 90 miles apart, and it takes 2 hours to get there. And so if we were talking about what is our average velocity, we usually think about speed. We're talking about velocity now. We said, what's your average velocity? Well, you know that that's 45 miles an hour because you went 90 miles in 2 hours. But now, let's say here is a possible graph for our distance at any time. So when we think about what does that the average velocity graphically look like, well, in my time and distance graph, I finished at the point 2 hours, 90 miles, and I started at the point 0, 0 miles. And so when I'm talking about what is my average velocity, well, it's really just the average velocity is the slope of the secant line. And this is all reviewed from what we looked at in the last video. So again, this is further review of what we're going to start doing is paring this down and start developing an idea of the derivative. So what we're moving towards, we're trying to develop an understanding of the derivative. And for our examples, the derivative really is just the instantaneous velocity. The derivative always is instantaneous rate of change. Okay, so in the last example, in the previous page, we were looking at what happens when your velocity goes from, what's your average velocity from time 0 to time 2. Now we're looking in the second hour. So the same idea, if we're looking for average velocity, we can graphically depict this secant line, and the average velocity during that second hour is the slope of this line. So we get these points. We get the point 90 minus 40 over 2 minus 1. Again, that's coming from that this is the point 2, 90, and this is the point 40, 1. If we're finding the slope, we're able to find that it's 50 miles per hour. Notice that this speed is not the same as the average velocity over the entire time. In other words, we're going faster we're averaging a faster speed in the second hour. Okay. So what I mentioned is we're trying to develop an understanding of the instantaneous rate of change. So what we're going to do is start looking at smaller and smaller time intervals. So this is just a graphical depiction of what we did. Once again, if we're looking at average rate of change between 2 points, we're just looking at the slope of the secant line. So, like I said, now we're looking at shorter time intervals. Now we're just looking between the time 1 hour and 1.5 hours. So, if I wanted to find the average velocity in that time period, once again, we can draw the secant line and find the slope of the secant line. So in order to find the slope, we need to get 2 points. So we've got the point 1.5, 50, and 1, 40. So the slope there, 50 minus 40 over 1.5 minus 1, which equals 20 miles per hour. Interesting. In the second half, between 1 and 2 hours, we were going, between 1 and 2 hours, we were going 50 miles per hour. But in the shorter time interval, now we're only going 20 miles an hour. And graphically, we see that by having a less steep slope. Okay, now we're finding the average velocity between 1 and 1.25 hours. Again, further shrinking this time between the 2 points. So, draw a secant line and get the point. So we've got the point 1.25. Now we're going to need to estimate a little bit, and that's roughly 48. And here we've got the point 1, 40 again. So the slope is 48 minus 40 over 1.25 minus 1. And this is 32 miles per hour. So our average velocity, depending on the time interval, keep changing, and they keep changing because the slope of this line keeps changing. Notice that if you want to talk about it as the original curve, doesn't have a constant slope. Its steepness is changing. So what we've been doing is we've been taking, starting with our point A, and in this case our point was, at time 1 hour and 40 miles. And we've been taking points, at 2 hours, 1.5 hours, 1.25 hours. We're moving B closer to point A. Or in a more mathematical sense, here's the point A, here's the point F of A, and here's point A plus H, and its corresponding point F of A plus H. What we're doing as we move B closer to A, what we're doing is we're letting H approach 0, where H is this distance between them. And as we let H approach 0, we're starting to look at the velocity at A, just at A. And if we're talking about the velocity at just a point, this is my instantaneous velocity. So using this idea, we've got point A and A plus H corresponding F of A and F of A plus H. Before, what we're doing is we're just, in order to find the average velocity, we would say, well, it's just the slope. And to kind of see that our first y value is F of A plus H minus our second y value, F of A, all over A plus H, x value minus A. And that's where that H standing alone comes from, because the A's are going to cancel off. And that's for the average velocity. If I wanted to find the instantaneous velocity, once again, that's when we let B get closer and closer and closer to A. So B is getting closer to A. It's going down on the actual curve itself. So what I meant to do there is, the green line is my original secant line, and now I'm moving the point B closer and closer to A, and as it gets closer and closer to A, we start looking at the instantaneous velocity of A. And we did that by letting this H value here go to 0. And so this is saying we're looking at my slope, where H equals 0. Or not equals 0, but gets close to 0. So that arrow is getting close to 0. So going back to this curve, what is the instantaneous velocity of the car at 1 hour? Well, we did something like this in the last video. At 1 hour, if we're looking at the instantaneous velocity, we draw a tangent line. Because we're choosing point 1 at 1 hour and another point that's infinitely close to it, and drawing the slope between them, and that's just the tangent line. And here we're going to need to use a lot of estimation, so your answers will all be slightly off. But if I wanted to find the instantaneous velocity, the first thing I do is I draw this tangent line. The second thing I do is I find the slope, just like we were doing before, but now we need to pick the points. So here's one point at 1.25 hours, 50. Here's another point at 0.75 hours at 30. So the slope equals 50 minus 30 over 1.25 minus 0.75, which is roughly 40 miles per hour. So we found the instantaneous velocity graphically, and right now I'm not doing algebra angle, graphically by drawing a tangent line and finding the slope of that tangent line. Alright, so now let's think about just some actual math function. We've got the function 3 plus x squared. So you all know what that looks like. It's a quadratic that's been shifted up 3. So it's going to be something like that. And we want to find the average rate of change from 1 to 5. Okay. Well, in order to do that, let's define f of 1 and f of 5. This is my function. So f of 1 is 3 plus 1 squared, which is 4. F of 5 is 3 plus 5 squared, which is 28. So we could, show that here. Here's the point 1 comma 4. Here's the point. Now my graph isn't totally right, but let's just do that scale and say here's the point 5 comma 28, and I'm looking for the average rate of change. So I'm looking for the slope of this secant line. The slope of that secant line is 28 minus 4 over 5 minus 1, 24 over 4. Let's just leave it like that. And then the next question is find an equation for that secant line. Well, I want to find an equation for this red line, the secant line. So I know that I can use point slope form, y equals mx minus x1 plus y1. And I have 2 points to choose from. I can either choose this point or this point. And I know the slope. The slope we found right here. So I think it's easier to choose the smaller number point. So the equation for my secant line is going to be y equals m. Well, we found that. 24 over 4 times x minus x1. Well, that's that point. Plus y1. And here's an equation for my secant line. Now I'm going to stop this video and